The purpose for this assignment is to apply classical AI search algorithms to two different types of problems: geometric path planning and a symbolic constraint problem. The goal is to model each problem using formal search components such as states, actions, and path cost, and then evaluate how different algorithms perform. The key questions we focus on are how to represent each problem as a search problem, which algorithms are most appropriate, and how heuristics influence performance and optimality. In particular, we are interested in whether informed methods like A can reduce the search effort while still guaranteeing optimal solutions. To address these questions, we use a core AI concepts such as state space representation, successor functions, goal test, and path cost. We also compare uniform methods like breadth first search and uniform cost search with informed strategies like greedy search and A, using an admissible heuristic based on Euclidean distance.
For the experiment setup, we first gathered the key information needed to define each problem. For the path planning problem, we used the start and goal positions along with the vertices of the obstacles, which are modeled as convex polygons. We also applied visibility constraints, so the path avoids obstacles and uses Euclidean distance to measure the cost between points. For the missionaries and cannibals problem, we defined the initial and goal states, the bulk capacity, and the main constraint that cannibals cannot outnumber missionaries unless there are no missionaries present. We also used a state representation that tracks the number of missionaries, cannibals, and the position of the boat. Finally, for both problems, we defined the state space, possible actions, and the rules for valid transitions to ensure the search algorithm works correctly.
For the obstacle problem, we did not use the continuous state space directly since it is uncountably infinite. Instead, we restricted the problem to a finite visibility graph where the nodes are the start point, the goal point, and the vertices of the obstacles. The successor function is defined using visibility neighbors, meaning we connect two nodes, the straight line segment between them does not intersect any obstacle. The path cost is defined as the Euclidean distance between nodes, and this allows us to apply informed search methods. For the missionaries and cannibals problem, we define each state as the total of the number of missionaries, cannibals, and the boat position, and we generate the state space graph using valid transitions. We then use breadth first search with repeated state checking to explore the reachable state. The results in the obstacle domain, different search algorithms produce different behaviors. The breadth first search may find a path with fewer segments, but it does not necessarily minimize the total geometric distance. The uniform cost search guaranteed an optimal solution because it considers the accumulated path cost based on the Euclidean distance. The greedy path search often expands the fewer nodes, but it can return a longer path since it ignores the costs already accumulated. The asterisk combines both ideas and returns an optimal path while usually expanding fewer nodes than uniform cost search because the Euclidean heuristic guides the search toward the goal. Therefore, the A asterisk is generally the best choice for this domain. For the Majority Campbell problem, the breadth first search returns the optimal path within 11 crossings. This is because all actions have equal cost, making the BFS both complete and optimal. The analysis also showed that repeated states are a significant issue due to the cycles in the state space, so using graph search within a explorer set is essential to avoid revisiting the same configurations. And these are the graphs from both problems, validating the results.
For the path planning problem, we observed that continuous environments naturally lead to an infinite number of possible paths. However, we can simplify the problem by restricting it to just the start point, the goal point, and the corners of the obstacles, which allows us to build a finite visibility graph. Using this representation, we define actions as moving between visible nodes, use Euclidean distance as the cost and straight line distance as the heuristic. From our results, A star turned out to be the best practical algorithm since it remained optimal while expanding fewer nodes compared to uniform cost search. For the missionaries and cannibals problem, we represented each state using the numbers of missionaries and cannibals on the left side along with the boat position. By applying the safety constraints that cannibals cannot outnumber missionaries, we ensure that only valid states are explored. Using breadth-first search with repeated state checking, we were able to find the optimal solution in 11 crossings. This problem also shows why humans struggle with it, since the constraints create misleading choices and many paths that lead to dead ends. Overall, we learned that effective problem solving in AI starts with a clear state representation. We also saw that the same search framework can be applied to very different types of problems, such as geometric problems, planning, and symbolic puzzles. Heuristics play a key role in improving efficiency, especially when they preserve optimality, as in A-star. Finally, repeated state checking is essential in problems with cycles to avoid unnecessary exploration.
Regarding acknowledgements, there are not specific acknowledgements for this project, since all the work was complete by a team following the assignment guidelines. For credits and reference, the main source used was the textbook Artificial Intelligence, a Modern Approach by Stuart Russell and Peter Norvin, which provide the theoretical foundation for the search algorithms and problems formulations. Additionally, the follow with the AIMA style implementation approach to structure or code, and we use the assignment instructions and materials to guide the development and analysis of our solution. Overall, the reference allow us to connect the theoretical concepts with their practical implementation in both problems.